In this lecture we will study the black hole region in more detail, and in particular we will show that any causal curve starting within the horizon region eventually falls on the central singularity. Then we will construct the maximal analytic extension of the Schwarzschild solution, and to do this we will need to introduce another set of coordinates which continues the Eddington-Filkenstein construction by introducing a second null coordinate. Using this, we will show that the Schwarzschild solution describes an internal black hole, and we will study its regions. Finally, we will speak about astronomical black holes, the ways of their detection, and the orbits about these black holes. So let us start with the black hole region. So in this subsection we will show that nothing escapes the black hole region. At least, So in this subsection we will show that nothing escapes the black hole region, at least modeled by the Schwarzschild solution. Let us start with a few definitions. So first of all, we will define a causal curve. Causal curve is a curve whose tangent vector is everywhere causal, that is time-like or null. Next, let us define the time variability. We want to have a preferred time direction. So space-time is time variable. If there is such a causal vector field, which we will call a time orientation. If another vector field lies in the same, if another causal vector field lies in the same light cone as our time orientation, it is called future directed. If not, it is past directed. So a spacetime is time orientable if it admits a causal vector field, which we call T, with T, and we call this to be time orientation. Time orientation. So another causal vector let's call it X is future directed, past directed, if it belongs either to the past light cone or the future light cone of T. So for example, let T be the time-like vector field. So at least at this given point. So we can always pick such coordinates that it is 1, 0, 0, and this is T. So if we have X belonging to the to the same light cone as t, it is future directed. If we have y in the opposite light cone, y is past directed. So any other orientation either agrees or is the opposite of the given one. So any other orientation either agrees or is the opposite of the given one. So there are only two in total. Now, before we state before proving our proposition, let us describe the orientation. Let us describe the orientation on the Schwarzschild solution. So in the exterior we are free to pick the time molecular vector field as being the time orientation. So we pick t equals k equals d over dt, or in Finkelstein coordinates this is the same as d over dv. However, we immediately run into problem. For r less than 2m, where this Killing vector field becomes space-like. In the interior region, a natural time-like vector field is d over dr. So this is exterior. In the interior, we'll pick t to be plus or minus d over dr. We don't yet know which sign to pick because we want these two orientations to agree. And they must agree on horizon. So what happens on horizon? Well, we have the product of on horizon we have the product of the two, that is GGV times GGR equals to minus equals to plus or minus GVR equals to plus or minus 1. Now recall from the special relativity that if the two vectors belong to the same light cone, their scalar product must be negative. So therefore we choose the minus sign. So in interior. Good. So now, armed with this knowledge, let us do the proposition. Okay. So we have a proposition. So if we have a time like, so if we have a causal curve, which is future directed, causal curve, and we have that at some moment, and we have that it starts inside the horizon, then it must always stay within the horizon. Then it must always stay within the horizon. So then R of lambda for any lambda greater or equal than lambda naught. Okay, so let us write the conditions of the theorem. So first of all, let us call the tangent to the causal curve as v. So tangent. Let us start with future directness. So future directness means that v belongs to the same light cone as minus d over dr, which is the same as minus gr mu v mu, which equals to 1 minus 2, which equals to 2 minus gvr dv d lambda, which is minus dv d lambda. So from this it follows that dv d lambda is less than 0. Next, let us write the condition for the curve to be causal. So we'll call this collectively as d theta d lambda squared. So notice that this term is greater. So notice that this term is greater than 0, and this term is also greater than 0. This term is also greater than 0. So from this we find that dv d lambda times dr d lambda is less than or equal to 0. Now we have two options. First of all, So greater than 0. Okay, so we see that the first and the last terms are greater than 0, and from this follows that dv d lambda times dr d lambda is less than or equal to 0. Now we have options. So first of all, we can still have dr d lambda greater. We still can have dr d lambda greater than 0. This immediately implies that dv d lambda is 0 because it cannot be negative by the future directedness condition. And yes, so in future directedness, the inequality can actually be not strict if we allow for the curve to be null, because if we consider a product of two null vectors and therefore two null vector fields, their scalar product would be null. Now from dv d lambda equals 0, substituting this in the causality, we get that v is a null vector, and therefore we get that d omega t lambda is 0 as well. Okay, so speaking about the future directedness, I wrote here as strict inequality, but in fact we can put less than or equal to 0, if we consider the product of two null vectors. So where d over dr is a null vector, and that is on the horizon, and where v is a null vector itself, the product of the two null vectors can be null. The product of the two future directed null vectors can be null. Otherwise, if at least one of them is time-like, the product would be negative. So therefore, we find that v is null, d omega d lambda is 0 as well, and then it follows that v is actually so the d over dv and d over d angles coordinates are absent, and v mu is 0, dr d lambda 0, 0. So in other words, v equals to dr d lambda minus dr d lambda minus d over dr. Now we will assume that dr over d lambda is positive, so this thing is less than 0. So we have that v is a negative multiple of the positive time-like orientation, and therefore it is actually path-directed. Next, if we have dr over d lambda less than or equal to 0 for r less than or equal to m, okay. So now we can have a second option. We can have that dr over d lambda is equals 0 also in the region where r is less than 2m. However, looking back at the causality, we will then necessarily have that, so we will necessarily have that all other components must vanish as well, because the rest are positive. So the dv or dv lambda component is positive, and the angles are also positive, and this is 0. So from this we find that dv d lambda equals d omega d lambda equals 0. So therefore v is identically 0. Therefore v is identically 0, which is not physically reasonable, and therefore we exclude it. So in other words, we have shown that everywhere in the interior region the radius will decrease monotonically. This proof can be then carried further, so that we can actually show that for any causal curve starting inside the horizon, the fall would happen in finite time. That is dr over d lambda. That is dr over d lambda is bounded from below, and is non-decreasing as well. Before continuing the study of the black hole region, let us stop and discuss astronomical black holes and the ways they can be and they were detected. So black holes themselves have a number of important observational features. First of all, they are very heavy but very compact objects. As we said in the first lecture, a black hole of the roughly solar mass would have its radius, or it will have its radius of several kilometers. Okay. Secondly, black holes are highly rotating objects, which leads to a number of phenomena which can be taken as observational hints to look for them. A good example, for example, we can have jets from supermassive black holes that can be significant on the level of the galaxy as well. So finally, the black holes, as we have just shown, they are not luminescent. They do not classically radiate, and the hypothetical Hawking phenomena is first of all still hypothetical, and secondly extremely weak. So therefore, we can potentially see the black hole only if it's surrounded by the luminous matter. For example, gas clouds, or another star, or another black hole, or another star, or another black hole. In the latter case, we are not speaking about the electromagnetic waves, but we're speaking about the gravitational waves coming from the merger. So, in principle, all astronomical techniques. So, in principle, all current astronomical techniques fall in one of the three categories. So, we can try to detect the X-ray. We can look at the radio diapason, and we can study the gravitational waves. There are also other hypothetical effects. There are also other hypothetical possibilities. For example, the possibility of observing the microlensing, but these things are still under development. So, microlensing, which can be observed by the electromagnetic radiation in other spectrums, possibly even the invisible spectrum. So, currently the leading installation for X-ray observations is the Chandra X-ray Observatory. And so Chandra X-ray Observatory. The X-rays come from the accreting process. So typically, this comes from binary systems, where a heavier black hole is slowly accreting mass from its companion. So this comes from black hole accretion. The radio astronomy. The leading installation in radio astronomy is the Event Horizon Telescope. And it can see, for example, the people are usually looking for some highly rotating ionized gas clouds surrounding the black holes. This is actually how the black hole in the center of our galaxy was found, the Sagittarius A. So the gravitational wave observations speak for themselves. Usually we observe for some heavy mergers, for example, some neutron star, or black hole neutron star, or black hole mergers, and we see the characteristic picture of in spiral, merger, and then ring down. That characteristic chirp signal that was found in 2015, first gravitational wave observation, first gravitational wave from black holes observation. So, what kind of black holes are there? So we can have supermassive black holes. So we call black hole supermassive. It is less if it's greater than roughly 100,000 masses of the sun. So we would typically see these black holes were seen. So we know a few, and they're typically observed either by the Kepler orbits, of other luminous objects, for example, stars, and this is actually how we discovered the supermassive black hole at the heart of our galaxy, or by the black hole shadow that affects the observational data coming from other galaxies. So we have Kepler orbits, and we have black hole shadow. Next, we have what we would say intermediate black holes, intermediate in a sense between supermassive and stellar-sized black holes. So we have masses is 10 to the power of 2 to 10 to the power of 5 solar masses. So we also know a few. And these are typically seen either by heavy mergers. And these are typically seen by the heavy mergers. So gravitational waves from finally, we have stellar-sized black holes. So these are from 3 to 10 to the power of 2 solar masses. So we have seen a lot. So we have seen a lot of this kind, and these were observed either by seeing the black hole accretion or by the gravitational waves. These are the three kinds of known black holes. There are, of course, other hypothesized classes of light black holes. So one of the most worthy of mention are the primordial black holes. So these are roughly 10 to the power of 11 to 10 to the power of 31 kilograms. We haven't seen them yet. So these primordial black holes are remnants of some stellar-sized black holes that were created in the early universe. So this is an interesting. So these black holes bring an interesting possibility to be observed by the Hawking radiation. So we will not cover this. We will not cover the Hawking radiation in this course, but the black holes radiate. But the black holes radiate as a black body by the quantum processes, and the smaller the size of the black hole, the more intensive its radiation and its evaporation becomes. So while for the supermassive black hole, the Hawking radiation would possibly be non-observable, for primordial black holes, they can become sufficiently strong to be potentially observed. So we have Hawking radiation or microlensing. To conclude, there are also other more speculative types of black holes. For example, we can speculate about black hole formation at the Large Hadron Colliders, but these black holes were, of course, have not been observed. And for some intermediate type of black holes that are between the primordial and microscopic black holes, there is no known mechanism, no possible mechanism of their formation is known. So these black holes remain in the speculative realm. Now, after finishing with the observational physics, we are firmly set on getting the complete description of the interior region of Schwarzschild solution including the black hole region. So the first step here is to introduce, the first step here is therefore to introduce another coordinate that will uncover an unexpected region inside the Schwarzschild geometry, the white hole. So, as you recall, we have just introduced, in the previous lecture, we have introduced the ingoing Eddington-Finkelstein coordinates. Now, what if we instead consider the outgoing radial null geodesics? So, let us introduce the U equals to T minus R star. In comparison, we had V equals T plus R star. Going, and these are outgoing. So the outgoing radial null geodesics are described by U equals constant. Now, let us rewrite the metric. Let us write the metric in this coordinate chart. So we have ds squared equals to minus 2m of r d u squared plus or minus 2du dr plus r squared d omega squared. So the sign here is minus, and as compared to the ingoing in the Eddington-Finkelstein chart, we had a plus sign there. So as we can see, this metric has similar properties to the ingoing Eddington-Finkelstein coordinates. So the metric is smooth and non-degenerate everywhere outside R equals 0, and therefore metric is, so in particular metric is smooth on the horizon, and therefore it describes it. So we will also have that the curvature is smooth at R equals to m, and therefore this chart describes not only the exterior but can also be extended into the interior as well. The R equals 0 is a curvature singularity, as seen from the TU squared term. So the question is, we see this, so R greater than 2m is of course the exterior, because we have introduced this chart using R star, and R star clearly has two regions, and it is well defined for R greater than 2m. So the question is, does the region R less than 2m describe as the black hole again? And the answer is actually no. So let us again consider the outgoing radial null geodesics, but within the interior region. So again, we have that outgoing radial null geodesics described by U equals to some constant value. Now, as we recall from the previous lecture, in the Schwarzschild coordinates, the radial null geodesics. The radial null geodesics are actually described as dr d tau equals to +1. So from so therefore we have that R is increasing, which is something unexpected. Because for the black holes, as we have shown before, the R must keep decreasing as the time or the parameter along the geodesics goes. So therefore, we have physically a different region where the radius keeps increasing with time evolution. So maybe, is it just related to so how can we explain it? Is it related to the time orientation? Maybe we have oriented the time in the opposite direction. And yes, it is connected. And it is a nice exercise to check that the time orientation that agrees in the exterior is defined by plus d over dr. So time orientation is given by, so exterior, in exterior we have it given by k equals to d over dt equals d over du, and interior it is given by plus d over dr. So this is as compared to ingoing Eddington-Finkelstein, where we had minus d over dr. Good. So we call this region to be the white hole. So the white hole as being the opposite of the black hole. We have the initial singularity, r equals to 0, which is obviously a curvature singularity. But we have the outgoing geodesics leaving it. So we can repeat the argument we did for the black holes, where we have shown that the singularity lies to the future of all possible causal curves. And here, we can derive a similar statement that the curvature singularity, r equals 0, lies to the past of all possible causal curves. So, in other words, we have geodesics and causal curves in general, leaving the initial singularity and then going to infinity. And there is no possibility for them to come back, to return. So, this region is, as you said, called the white hole. And the question is if this region is actually physical. We don't expect it to be physical for many reasons. One of the most straightforward ones is that, well, we expect that the black holes that form as a gravitational, that have a mechanism of formation, the gravitational collapse, we expect them to be stable solutions. Stable, it means that if we do small perturbations, they will initially settle with the time evolution. Now, since the white hole is essentially the time reverse of the black hole region, we will have the opposite. We will have the small fluctuations will, instead of being suppressed, will grow with it as the time evolves. So white hole is essentially unstable. So now we have shown that the Schwarzschild solution has not only the black hole, including both the exterior and interior, but also white hole. So the question is how these regions are related. And to describe the whole picture, we will need to use both coordinates, both of the Eddington-Finkelstein coordinates. So let us define the Kruskal coordinates, the Kruskal-Shekarash coordinates. By u equals to minus for m, and the capital V equals to V over 4m, where u and V are outgoing and ingoing Eddington-Finkelstein coordinates. So therefore, we have that u is less than 0 and v is greater than 0. Note that we can recover the time and the radial coordinates from the u and v by, so u times v equals to minus epsilon rho star over 2m equals to minus and the time coordinate by v over u equals to epsilon to minus, so to minus exponent of 2 over 2m, 2 over 2m, good, 2 over 2m. So notice that in the exterior region, the T and R and U and V coordinates are in one-to-one correspondence. So we have that the function R of UV is well defined. For u less than 0, v greater than 0. So in the exterior region. Similarly, T of u and v is also well defined. Good. So now let us write the metric. So as an exercise, I'll ask you to check it. So in terms of new coordinates, the metric is written by where R is understood as a function of u and v. We can take a formal definition for the function r of u and v to extend it to different regions. So, for example, if you consider the opposite region, if we consider the region u greater than 0, v less than 0. So we can again take the let's call it star. As a formal definition. So notice that in this case we will also have the region corresponding to r greater than 2m. So there. So this is like the second exterior region. So this is like the second exterior region that we have. Now, let us consider what happens when either u or v, but not the both, change the sign. So if we have, now let's have u greater than 0, v greater than 0 as well. So then we have that the left-hand side is positive, and therefore the bracket here is negative. So we have r greater than, we have that r is less than 2m. So this region would then correspond to the interior, either of a black hole or of a white hole. Similarly, we'll also have r equals r less than 2m. We will now need to distinguish which region corresponds to a black hole and which region corresponds to the white hole. We will study it. We'll study it just now on the diagram. First of all, but before, let us consider the bifurcation regions. So, what happens where either u or v or both equal to 0? So we have that if u times v equals 0, then r equals to 2m. So this corresponds to the horizon, either of a black hole or a white hole. But notice that this is not the one, but two surfaces. So two surfaces, u equals 0 and v equals 0. These two surfaces intersect at a single point, u equals v equals 0. And this point we would call the bifurcation point, because this point lies at the center, at the intersection of all regions. Good. So the last step before drawing the diagram would be to consider where does the curvature singularity lie. So the curvature singularity, r equals 0, would correspond by this formula to, u times v equals 1. So this is, so as we see, this is a hyperbola consisting of two branches. One is when both u and v are positive, and the second one is when u and v are both negative. So as you see, in this way, we have formally defined the metric for any values of u and v in R. So we have defined the metric for any u and v for any real values of u and v. Okay, good. So let us start with the diagram. So we have two lines. So this is the v-axis, and this is the u-axis. So the lines of constant u and v are given by straight lines. Now, as we recall from the coordinates, the constant time slices are given by v over u equals const. So that is t equals constant. So constant time slices would correspond to lines through the origin. So what are the constant R surfaces? So constant R surfaces would correspond to this kind of hyperbolas. So in the exterior region, they would be given by this. So R equals constant. And similarly in this region as well. Now, in the interior regions, we'll have similar picture. So, in particular, the curvature singularity corresponds to R equals 0, and therefore lies. So, this is the line R equals 0. So the horizon corresponds to two surfaces, u equals 0 and v equals 0. So this is the horizon, R equals to m, and R equals to 2m. Good. So let us name the regions, and let's study their physics. So let us title the regions starting from the. So let us name the regions starting from the most physical ones. So this is the region number 1. Region number 1. This is the region number 2, 3, and 4. So which region does correspond to which geometry? So the first region is clearly u less than 0, v greater than 0. So this is the Schwarzschild exterior. If you consider the geodesics in this region, so for simplicity, let us consider the radial null geodesics. So if we consider the ingoing radial null geodesics, we would have lines of constant v. So this is eventually falling onto the singularity in the second region. So ingoing radial null geodesic, and the outgoing radial null geodesic will go as so notice that in region 3 we can formally continue this line to the singularity. So this would suggest that the region 3 would correspond to the white hole. Okay, so yes. So the region 2, which corresponds to u v greater than 0, corresponds to the black hole. So to the black hole, because the curvature singularity lies to the future of all causal curves. The third region is the time reverse of the second one. So we get it by inverting the signs of u and v. We have u and v less than 0. And this is the white hole. This is the white hole because the curvature singularity lies to the past of all possible causal geodesics. Good. So what about the fourth region? This region is a bit mysterious. So again, this corresponds to r greater than 2m. So it describes some exterior region some exterior region. So in particular, the causal curves can easily escape to their own asymptotic infinity. So finally, we have this mysterious fourth region. So notice that, again, this corresponds to some exterior in the sense that it corresponds to the value of radius greater than 2m, and we have the causal curves, and we can have causal curves escaping to the infinity. So the question is, what is the nature of this exterior region? Is it another universe? Can it be connected to the first one? Is it its time reversal? Good. Is it its time reversal? Let us again look at the geodesics in this region. So the lines of constant u would go, so u equals constant, would then go inside the black hole and eventually reach the singularity. So reach singularity. So, however, there is no possible causal curve that can go into the region 1. However, the regions 4 and 1 are not entirely causally disconnected, in a sense that the in sense that the matter falling into the black hole, going to the region 2 from region 1, will meet with matter going from the region 4. So the region 2 and the region 4 are connected by the black hole. Are connected to the black hole in the future of some of their causal curves. Similarly, the white hole connects is the common region for the past of some causal curves of region 1 and 4. So the region 4 corresponds to u greater than 0, v less than 0, another exterior. And so the regions u, so the regions 1 and the region 4 are actually isomorphic by u v going to minus u minus v, to u minus v. There is no possible, so again, just to emphasize, there is no possible causal connection because the only possible, because the only intersection between these two regions would be the point u equals v equals 0. This point. This point. However, this point, as we have shown, corresponds to a particular value in these coordinates. So notice that u equals v equals 0 is the intersection of two surfaces. So this is the bifurcation point and the bifurcation region connecting both the white hole and black hole and the two exteriors. Now, okay, so one last comment would be, well, of course, be about the black hole region and the white hole region. So notice that in the second region, the singularity lies to the future of any possible causal curve. So effectively, the radial coordinate becomes the time coordinate. So the black hole region becomes the time dependent. The d over dr plays the role of time, and effectively the region 2 corresponds to a homogeneous anisotropic universe approaching a big crunch. Similarly, the region 3 is its time reversal, so it's a homogeneous anisotropic universe appearing from a Big Bang. Appearing from Big Bang. Good. So naturally, the first question that we come with when seeing this diagram is which of these regions are actually physical, and let us consider the collapse of a real star in the u and v coordinates. So the diagram for the real collapse would look like something. So we have v, we have u. So the center of the star being at first the center and then becoming the singularity would have the world line going like this until the singularity actually forms, and we have this. So r equals 0, and this point corresponds to the singularity formation. So the boundary of the star would first be visible to us before falling behind the emerging horizon. So we would have going like this. So total, we have that interior. Of the star. So the only physical regions are the region 1 and the region 2, and part of the region 2. Okay, so finally, let us discuss the time translation in Kruskal coordinates. So we can show that K, the stationary Killing vector field, is given by 1 over 4 m v dv minus u d u. So we have that k squared equals to minus 1 minus 2 m r. So we can notice that this Killing field, this Killing vector field, degenerates at the u equals v equals 0. So emphasizing the nature of the bifurcation point. So we have the bifurcation point. And at this point, the time direction is, the time orientation is not well defined. This is the point where the time orientation between the regions changes. So, question: can we somehow manipulate the question? Can we study what goes on with the constant time hypersurface going through the bifurcation point? This is the next subsection. So we have the sigma tau, the time equals constant hypersurface. Time equals constant hypersurface corresponds to the line in the u and v coordinates. So line in u v coordinates that goes through u equals v equals 0. Through the origin. So going through the origin, which is the bifurcation point. So it is convenient to introduce another radial coordinate to study the geometry. So let us introduce the rho, the isotropic radial coordinate. So of course, for a given value of r, we find that rho is multiply defined. There are two branches. So if you do the plot, and this is rho, this is r, we have that for that to a given value of r, there corresponds two values of rho. So we will choose that this region is region number 1, and this region would correspond to region number 4. So this is region number 1, and 0 rho. The metric is now written as ds squared equals to minus 1 minus m over 2 rho theta squared 1 plus m over 2 rho plus 1 plus m over 2 rho to the power 4 g rho squared plus rho squared g omega squared. So as you see, here we effectively have the Euclidean space-time times a conformal factor. So this motivates the name isotropic. So the constant time slice, corresponding to the constant value of the coordinate c, would then be this part of the metric. So this is ds of. So this is the induced metric on the constant time slice. The constant time slice. So let us now draw the diagram. So we have two asymptotically flat regions. So we have two asymptotically flat regions connected by the throat. So this region corresponds to r going to infinity, and this region corresponds to r going to 0. They're connected by the throat. So the narrowest part of the throat, happens at rho equals to 1/2 of m. So rho equals to m over 2. So the minimum, and in usual Schwarzschild radial coordinate, this is the r equals to m radius. So this geometry, this through geometry, is called the Einstein-Rosen bridge. And sometimes there is a popular misconception that since Schwarzschild geometry describes Schwarzschild geometry in Kruskal Shekarash coordinates describes two different asymptotically flat regions, there is a way to transverse them, so there is a wormhole. However, as we have just shown, there is no direct communication between the region 1 and the region 4. The signals from this region can only meet in the black hole region, from which you cannot live. So this geometry, the Einstein-Rosen bridge, is an example of local asymptotically flat geometry because it has two asymptotically flat ends. So let us sum up what we have just seen in one simple definition. So we have just shown that the Schwarzschild geometry can in fact be extended by the introduction of appropriate coordinate chart until we have reached the maximal analytic extension. So we'll have a space-time, so we can call a space-time extendable if it is a proper subset of a larger space-time. So we have seen that Schwarzschild R greater than 2m is extendable, and the full space-time, the full Kruskal space-time, is inextendable. Good. So this, of course, this definition is, of course, not particularly constructive. So how can we study if the space-time is actually extendable or not? Well, we studied the space-time by the causal curves, by the causal geodesics. So recall that geometrically, a curve is just a smooth map. From the path of the real line to the manifold. So sometimes the curve can be extended. For example, if we have just dropped the curve halfway and it doesn't actually reach any feature of the space-time. So in these cases, we call that the curve has an endpoint. So a bit formally, we can write it as the point P of the space-time is a future endpoint of a future-directed causal curve gamma, if for any neighborhood O of the point P, there exists such T naught such that gamma of T belongs to this neighborhood for all T greater than T naught. So we'll call gamma to be future inextendable if it doesn't have such endpoints. If no future endpoint. Similarly for the past. Similarly for the past endpoints and past inextendability. So this is done to exclude the trivial case where the curve is extendable simply because it has been dropped for finite parameter value and it doesn't reach any feature. So let us now formulate one of the criteria by which we can call the spacetime to be complete. So let us study the geodesics. So geodesic is complete if it doesn't have any if an affine parameter of the geodesics extends to infinity. If its affine parameter extends to plus or minus infinity. So a spacetime is called geodesically complete if all geodesics can be extended. If all geodesics are inextendable. All causal geodesics are inextendable. A spacetime is geodesically complete if all inextendable causal geodesics are complete. So a good example is the Minkowski spacetime. Minkowski spacetime, where in the absence of any features, every geodesic, every geodesic that is inextendable, every causal geodesic that is inextendable, is complete. A counterexample is, of course, the Schwarzschild spacetime, where an ingoing geodesic would meet the singularity in a finite value of parameter, in a finite value of the affine parameter. So therefore, we see that the presence of some features of the spacetime, such as singularities, makes the spacetime to be geodesically incomplete. So where can a geodesic potentially end? Well, speaking about the where geodesic can potentially end. So again, we will speak about the inextendable geodesic to exclude the trivial case where we just drop the geodesic halfway. So it can end either on some features of the space-time, or it can go to the infinity. In the case of infinity, in the Minkowski space-time, we are safe. So we can show that for asymptotically flat spacetimes, that is for the spacetimes that approach Minkowski at infinity, for every causal geodesic, the affine parameter would safely extend to plus or to minus infinity. However, in general, this is not the case, and it is a nice exercise to show that for the anti-de Sitter spacetime, radial null geodesic reaches the asymptotic boundary in finite time. So we have ADS4 given by ds squared equals to minus hyperbolic cosine of rho dt squared plus r squared, where r is a constant, which is called the ADS length, times d rho squared plus hyperbolic sine d omega squared. So this is the S2, this is constant. So, and rho runs from 0 to plus infinity. So for outgoing radial null geodesics, so they approach d infinity at finite value of the coordinate time. So at pi over 2 times r. So the hint is that the geodesic equation reads as hyperbolic sine of rho equals to trigonometric tangent of time over the ADS length. So this is a notable counterexample, and in the asymptotically anti-de Sitter spacetimes, it is treated by introducing a particular set of the boundary conditions, which are called reflective boundary conditions. In general, this behavior of the ADS motivies its understanding as being a box, in the sense that it is a box of finite size, at least for massless geodesics. But in this course, we will not consider the ADS spacetimes any longer. Let's finish with the possible description of features on which the geodesic can end. So these features are the features where the metric stops being smooth. So these features are essentially called the singularities. So we would write the definition of the singularity as the region for so singularity in general corresponds to a region where metric is a degenerate or non-smooth. So this can either correspond to coordinates, but as we have shown, it can be coordinate singularities, but these can be reduced by introduction of appropriate coordinate chart, or it can actually correspond to curvature singularities, which we have also discussed before. So for the curvature singularity, the geometric invariants, for example, the scalars of the curvature tensor, diverge. There are also examples of the singularities where all possible scalars constructed from the curvature tensor are regular, while some of the components, some of the non-diagonal components, still diverge. This is a different kind of singularities, which are called directional singularities, and they can correspond to, let's say, to tidal forces acting on a falling string. Finally, there are geometric singularities that do not necessarily correspond to curvature singularities. And a typical example is a non-smoothness due to conical deficit. So as you recall, in the first lecture, we have used the smoothness of the space-time around zero to obtain the value of the mass of the cold star. So we have said that we want the geometry to be smooth at zero, and in particular, it should be devoid of any possible conical deficits. So a typical example of the conical deficit would be a metric of the form, let's call it dr squared plus lambda squared r squared df squared, where lambda is a constant. So if lambda equals to 1, to plus or minus 1, we have the description of the two-dimensional plane in polar coordinates. And we have phi running from 0 to 2 pi, so there is no conical deficit. However, if lambda is different from this value, we will have to So we will have to redefine the angular coordinate. So we will have to introduce lambda phi such that the geometry is locally written as dr squared plus r squared d phi tilde. Again, this is locally smooth for all this is locally smooth, but the period now has a conical deficit. And as you recall, every Riemannian and by extension a pseudo-Riemannian manifold is locally smooth in the sense that when we construct the manifold from the chuts, the chut is defined by a map from some neighborhood of the from some open neighborhood of the manifold to Euclidean spacetime, which defines the coordinates. So as we see around the axis, around r equals 0, we cannot define such a neighborhood for all values of the angle phi tilde, if you consider phi tilde to be because for a smooth geometry phi tilde needs to run from 0 to 2 pi. So this defect circumference is called the conical singularity. Good. So in the next lecture, we will study. So in the next lecture, we will study the possible deformations of the black hole geometry, which corresponds to the initial value, which corresponds to the initial value problem for black hole spacetimes.